Welcome guys and gals to this tutorial of JMT in which we will implement a simple open model consisting of a single queue station. We evaluate the impact on performance indices of some modifications of the workload and we use the JMVA tool. The model is this one. We have a queue station, jobs request arrives with arrival rate lambda, are served with service time S, and the solution algorithm adopted is the open queuing network, are the open queuing network equations. Let me remark that in spite of their simplicity, models with a single station yields in many cases interesting results. For example, if we consider a complex system, this station, the station of the model may represent a resource that is highly utilized, much more with respect to the others, and thus that is largely responsible for the overall system performance. As a consequence, models with only these results will provide accurate predictions of the performance of the entire systems. The system has been measured for 2 hours, and from the number of requests executed C divided by the length of observation interval, we obtain the arrival rate that is 2 requests per second. Let me point out that the assumption for the workload is that it consists of a single class of requests. That is, all the requests executed by the system have similar characteristics, and thus their service demands can be described with their mean values. The mean of all service time is S, so 100 milliseconds, and the distribution assumed is exponential, are exponential either interarrival and service time, and we also study the usual performance indices.
I have a question. How can I compute the performance indices of the server with the actual workload?
Well, in this case, we should open the model, so we start to implement the model. This is the first window of JMT, and now we select MVA. Let me resize the window selected, and so we have this window where the class is by default closed, and so we have to select the open model, and automatically the algorithm selected will be queuing network, and we have to also set the correct value of arrival rate, that is 2. The next parameter is the station name and the station type. Type is queue, because it may be we have a possibility to select a delay, and queue. Queue is load independent since the model is open. That means that the service time is independent on the number of jobs the number of requests that are in the station. The next parameter is the service time, so we have 0, 1 to select, and the next one is the number of visits. In our simple case is 1, and the reference station is the arrival process. This is the station used to compute the system throughput and response time. In this simple model it is clearly straightforward, but in more complex models it must be selected very carefully. We may solve now the model, and here is the window with the performance indices. With the throughput or arrival rate of 2, we have number of customers 0.25, system response time 125, utilization is 20%. We may check these results because analytically it's simple to obtain them, and you may see that in this case we have 20%, under 25, and 0.25 request in the station. Those coincide with the one provided by the model.
I have a question. How can I study the behavior of the performance indices with arrival rates ranging from 0 to 9.9 requests per second?
Okay, so here 9.9, let me point out that this 9.9 is close to the maximum arrival rate before the saturation. And indeed, the lambda rate that saturates the system, the lambda arriving rate that saturates the system is 10, is 1 over s. So practically we want to have all the value with all the possible lambda. Let's consider again in this case the model. Here we have not selected before the what if. What if is a powerful feature that once enabled, like now we enable and we select as a control parameter arrival rates. We may select also others, for example service demands. Well, arrival rate means that all the number of models specified here will be solved changing the control parameter arrival rates. So here we want to select the arrival rates ranging from 0 practically. So let's start to select the starting arrival rate 0.1 and go to define, let's go to define the final arrival rate, that is 9.9. Let's consider 100 values of lambda between these two extreme values and solve this, and we have the possibility to see all the results in graphical way or in textual format. So if we select, for example, the system response time, here you may see the behavior of the system response time for all the ranging for all the values of lambda. Or we may select the utilization. We should select which station, station 1 here. As you may see, we go close to 1 saturation as we anticipated before, or the system number of customers, okay, these ones. So leave the system response time in this case. So we have all the values that we want to obtain. Textual results provide the value of all these parameters in textual form. Okay, now let's
I have a question. Which will be the maximum arrival rate in order to have a mean response time of 2 seconds?
Well, for this question, we should consider again the curves we obtained before. We want to know which is the arrival rate, maximum arrival rate corresponding to mean system response time of 2 seconds. From the graphs, we may see this one, but it is more precise to consider the textual results. We go here and let's select the 100, the results corresponding to 9.9, and let's consider system response time. So for 9.9 arriving jobs per second or requests per second, we have 10. Now let's consider to decrease 9.8, 7, 9.6. Here you may see, okay, with 9.50 we have 2.01, and with 9.4 we have 1.6. So the answer to the question is 9.5 arrival rate. This value can be also obtained in different way when we run simulation, but also in this simple case of this simple model we may obtain it analytically, because let me point out the analytical verification. We have from the formula of response time, that is s over 1 minus lambda s, knowing that r should be 2 seconds, as it should be 0.1 seconds, we may derive lambda. Lambda in this case is 9.5. That coincides with the value that we obtained with the model. Well, we have completed this simple tutorial. In the next one we will solve the same model with simulation, showing all the new possibilities that the simulation technique offer. We hope you enjoy JMT. See you soon. Best regards.